Okay, so in this problem, we're given the values of two charges, and we're asked for the electric force exerted by Q2, on Q2 by Q1. So we're looking for the force that Q1 exerts on Q2. Now notice that the question tells us that these two charges have opposite polarities. So Q2 is negative, while Q1 is positive, which means that the electric force acting between the two charges will be attractive. So the force exerted on Q2 will be towards Q1. Consequently, Q1 will be attracted to Q2 with the same magnitude of force, just of course in the opposite direction. And these two forces are a Newton's third law pair. Okay, so let's begin writing down what we know in this question. We definitely know that we're going to have to use Coulombs Law, which tells us that the electric force is the Coulomb constant times the charge of one object times the charge of the other divided by the distance between them squared. Coulomb's constant should always be known. It's 9 times 10 to the power of 9 Newton meters squared per Coulomb squared. So if you don't know that by heart, you can presumably write it down before you go into an exam, or maybe you'll be provided with a formula sheet that has this constant. Okay, and then the question also gives us Q1 and Q2. I'm not going to bother to rewrite them since the question gives them as Q1 and Q2. And then we're also given the distance between the charges, 0.75 meters by the diagram. So R is 0.75 meters. So now we can plug some things into our formula here. So the electrostatic force will be Coulomb constant, 9 times 10 to the power of 9 Newton meters squared per Coulomb squared times Q1, given by the question as 1.2 times 10 to the power of minus 9 coulombs times Q2, negative 2.7 times 10 to the power of minus 9 coulombs, divided by the distance between them, 0.75 meters squared. It's ugly. There we go. So quick check on the units here. A Coulomb squared in the denominator cancels with coulombs times coulombs, which is Coulomb squared in the numerator. And then meters squared in the numerator cancels with meters, which is being squared in the denominator. So we're left with units of newtons, which makes sense because we're looking for a force. Okay, now if you plug this all into your calculator, you should come out with negative 5.2 times 10 to the power of minus 8 newtons. Now this negative indicates that the force is attractive. In this case, we've kind of already accounted for the direction of the force from our diagram. We already know the direction of that force, so we could have left this negative sign out of our equation, and we could get rid of it in our final answer since we know the direction. So if we got rid of this negative sign and we quoted the electrostatic force acting on Q2 exerted by Q1 as 5.2 times 10 to the power of minus 8 newtons to the right, that would be correct.